Imagine 10 people standing in a line, each wearing a hat they cannot see, forced to guess its color or be devoured by extraterrestrial captors. It sounds like a party game designed by a sadist. But this scenario, popularized by a celebrated puzzle, contains one of the most elegant mathematical insights ever discovered. The solution hinges not on luck or telepathy, but on a property of numbers, so fundamental it underpins the infrastructure of modern civilization. That property is called parity, and it is nothing more than the question of whether a number is odd or even. The puzzle works like this. 10 captives stand single file, each able to see only the hats ahead. Starting from the back, each must say black or white. If at least 9 guess correctly, everyone survives. The person at the back counts the black hats visible ahead. If the count is odd, that person says black. If even, white. This single word encodes the parity of all visible hats, giving every subsequent person enough information to deduce their own hat color with certainty. The first speaker has a 50-50 shot at survival, but that sacrificial guess guarantees everyone else gets it right. A single binary signal, 1 bit, cascades forward and rescues 9 people from doom. Hat puzzles trace their origins to at least 1961, when Martin Gardner began exploring them, and surged into academic prominence through Todd Ebert's 1998 doctoral dissertation at UC Santa Barbara, which formally connected them to coding theory. Parity is deceptively simple. Count the ones in a binary string. If the total is even, the parity is 0. If odd, it is 1. That single extra bit, appended to a sequence of data, becomes a sentinel standing guard over every digit that precedes it. In telecommunications, this mechanism is called a parity bit, and it has been protecting data transmission since the earliest days of digital communication. When a sender and receiver agree on even parity, every transmitted packet must contain an even number of ones. If interference flips a single bit during transit, the parity check fails, and the receiver knows something went wrong. Devices as common as SCSI and PCI buses use this technique to catch transmission errors, and many microprocessor instruction caches rely on parity protection to verify cache data integrity. The limitation is well understood. A parity bit can detect an odd number of flipped bits, but is blind to even numbers of simultaneous errors. 2 bits flip, and the count looks fine, even though the data is damaged. For channels where errors are rare and redundancy must stay low, parity adds just 1 bit per data word, a mere 12.5% overhead on an 8-bit byte, making it one of the most efficient error detection tools ever devised. It is the same logic at work in the hat puzzle. The person at the back compresses a complex visual scene into a single binary signal, and that signal propagates forward, updating itself with each new piece of information, just as a parity check propagates through a data stream, flagging anomalies 1 bit at a time. In the late 1940s, a Bell Labs mathematician named Richard Hamming kept losing his weekend computing jobs to errors in punched card readers. The Bell Model 5 relay computer could detect mistakes during the week when operators were present, but after hours, it simply moved to the next task, discarding hours of work. Hamming's frustration crystallized into a question that would reshape technology. If a machine can detect an error, why can it not also locate and correct it? By 1950, he had published his answer in the Bell System Technical Journal. His paper introduced what we now call Hamming codes, the first family of practical error-correcting codes. The core insight extended parity from a single check into multiple overlapping checks, each covering a different subset of bits. A Hamming 7-4 code encodes 4 data bits with 3 parity bits, producing a 7-bit code word. If any single bit flips, the pattern of failed parity checks points directly to the corrupted position, allowing automatic correction without retransmission. Hamming codes are mathematically perfect, achieving the theoretical maximum efficiency for their block length and minimum distance. They earned Hamming the Turing Award in 1968 and remain in active use today in ECC memory modules, satellite communications, and embedded systems. The connection to hat puzzles is not metaphorical. Ebert's doctoral work demonstrated that optimal strategies for cooperative hat-guessing games are mathematically equivalent to binary covering codes of radius 1, the same structures Hamming pioneered. A puzzle about hats and a protocol safeguarding your computer's memory share identical mathematical bones. Every photograph stored in the cloud, every financial transaction archived on a server farm, owes its survival to Parity. RAID technology uses parity calculations based on XOR logic to reconstruct lost data when a hard drive fails. RAID 5 distributes parity blocks across all member disks so that any single drive failure can be fully recovered. RAID 6 adds a second parity layer using Reed-Solomon algorithms, enabling recovery from two simultaneous failures. Industry best practices now recommend RAID 6 for drives larger than 8 terabytes because extended rebuild times increase the vulnerability window. A 2025 survey in ACM transactions on storage traces the evolution from classical parity-based RAID to modern erasure coding used in hyperscale data centers, where petabytes of information must survive constant hardware churn. In quantum computing, the fragility of qubits demands error correction far more aggressive than anything classical systems require. Quantum low-density parity check codes, or QLDPC codes, borrow the structural logic of classical parity checks and extend them into quantum Hilbert space. In 2025, researchers at the Institute of Science Tokyo developed novel QLDPC codes approaching the theoretical hashing bound while scaling to hundreds of thousands of qubits, a breakthrough published in NPJ Quantum Information. That same year, a team using a 3-2 qubit superconducting processor demonstrated the first hardware implementation of distance, 4 bivariate bicycle codes, with results published in Nature Physics. Parity, the humble, odd or even check, is now helping build the computers of the future. The hat puzzle endures because it captures something profound about how information works. A single bit, a lone yes or no signal, can unlock an entire chain of correct decisions if everyone in the chain knows how to interpret it. This is not just a principle for computers. It is a principle for teams, organizations, and any system where individuals must act on incomplete knowledge. The puzzle demonstrates that cooperation does not require everyone to share the same view. It requires only that everyone agrees on a protocol, a shared framework for interpreting signals. The person at the back cannot help themselves, but their sacrifice creates a cascade of certainty for everyone else. Research into hat puzzles continues to push mathematical frontiers. A 2025 paper on the ArcSieve explored probabilistic bounds on infinite player hat-guessing games, proving that measurable strategies cannot achieve the success rates available through non-constructive methods relying on the axiom of choice. Meanwhile, the three-hat problem and its variants remain active areas of combinatorial research, with optimal strategies still unknown for most player counts exceeding 9. These are not idle curiosities. Every advance in understanding cooperative guessing games feeds back into coding theory, which feeds into the error correction systems that keep the modern world running. The next time you hear a riddle about prisoners in colored hats, pay attention. The math inside that whimsical scenario is the same math that guards your bank records, preserves your family photos, and may one day power a quantum computer capable of feats we can barely imagine. The aliens, it turns out, were testing something real. The outro scene features a dynamic slideshow illustrating the core concepts discussed from the initial hat puzzle scenario to visualizations of binary codes and Hamming's work. A calm, reassuring voiceover explains how seemingly complex puzzles like the extraterrestrial hat game are rooted in fundamental mathematical principles like parity, showcasing its surprising applications in everything from data storage to cutting-edge quantum computing. The visuals emphasize the elegance and interconnectedness of these concepts, leaving viewers with a sense of wonder at the power of mathematics. We thank you for watching and invite you to leave a like and share your own experiences or hidden gems in the comments below.